Lesson 1. Introduction to the Respiratory System. Imagine, for a moment, that you are sitting by a quiet lake at dawn. The world is perfectly still, and the only sound is the soft rhythmic pull of the air entering and leaving your body. You don't have to command it. You don't have to remind yourself to do it. Even as you drift toward sleep right now, your body is performing a miracle of engineering that has been running since the very second you were born. It is the most intimate connection you have with the world around you, literally taking pieces of the atmosphere and weaving them into your very blood. This is the story of your breath. And tonight, we are going to look behind the curtain at the magnificent system that makes it all possible. Welcome to our first session together. I'm so glad you've decided to settle in and learn something beautiful as you rest. My goal tonight is to be your guide through the grand architecture of the human respiratory system. We often take it for granted because it is so faithful, so silent. But as we explore this together, I think you'll find that the respiratory system is far more than just a pair of lungs. It is a masterpiece of physics, chemistry, and biological grace. We are going to start at the very beginning, the why and the how, to lay a solid foundation for everything else we will cover in this course. Think of this as the first chapter in the biography of your own vitality. In this opening lesson, we are going to establish the grand design. Before we get lost in the names of every tiny tube and membrane, we need to understand the fundamental mission of the respiratory system. We'll be looking at the 4 distinct processes that collective make up respiration. We often use that word to mean just breathing. But in a university-level study, we discover that breathing is actually only the first act of a much larger play. We will explore how the body bridges the gap between the air outside and the microscopic cells deep within your muscles and organs. Tonight is about the big picture, the logic of the system, and the essential role it plays in keeping your internal chemistry in perfect balance. To understand the respiratory system, we must first define its primary objective. Its main task is simple to state but complex to execute. It must provide the body with oxygen and dispose of carbon dioxide. This process, which we call respiration, is actually broken down into 4 very distinct steps that function like a relay race, passing the baton from the outside world all the way to your cells. The first step is what we call pulmonary ventilation. This is the mechanical process that most people simply call breathing. It is the physical movement of air into and out of the lungs, ensuring that the air inside those deep chambers is constantly being refreshed. Think of this as the ventilation system in a great library. It ensures the air never grows stale so that the work inside can continue. The second step is external respiration. This is where the world of the lungs meets the world of the blood. It's a beautiful silent exchange. Oxygen moves from the tiny air sacs in your lungs into the bloodstream, while carbon dioxide, the waste product of your life's energy, moves from the blood back into the lungs to be exhaled. This is a moment of profound transition, where the atmosphere truly becomes a part of you. The third step takes us into the realm of the cardiovascular system, known as the transport of respiratory gases. Here, the blood acts as a high-speed courier. It takes that freshly caught oxygen and carries it to the furthest reaches of your body, from the tips of your toes to the neurons in your brain. At the same time, It picks up the carbon dioxide trash from those areas and hauls it back to the lungs. Finally, we reach the fourth step, internal respiration. This is the mirror image of the second step. Here, the blood delivers its oxygen to the individual tissue cells and picks up the carbon dioxide they have produced. And as we look at this system, I want you to visualize it not as a static set of organs, but as a flowing, continuous loop. It is a bridge between the vast open sky and the microscopic internal sea of your body. The anatomy we will study in later lessons, the nose, the throat, the trachea, and the lungs, are all simply the infrastructure built to support these four essential steps. Take a moment to let that idea find its place. You aren't just breathing to fill your chest. You are breathing to feed every single one of the trillions of cells that make you who you are. If your mind is still following along, try to visualize that oxygen traveling like a golden thread, woven through the tapestry of your entire being. To truly appreciate why our respiratory system is designed this way, it helps to look back at the history of how we came to understand it. For a long time, ancient scholars thought the purpose of breathing was simply to cool the heart. They felt the heat of life inside and assumed the lungs were a sort of bellows meant to keep the internal fire from becoming too hot. It wasn't until the 18th century, with the work of brilliant minds like Antoine Lavoisier, that we realized the truth. Breathing is actually a form of slow, controlled combustion. Lavoisier discovered that our bodies use oxygen to burn the nutrients from our food, producing energy, water, and carbon dioxide. This chemical reaction is what keeps you warm and gives you the power to move and think. In this light, your respiratory system is the intake valve for the fuel of life. This is why we call the cellular process cellular respiration. It is the ultimate why behind every breath you take. Beyond just gas exchange, the respiratory system serves several other vital, silent functions that we often overlook. For instance, it is a master regulator of your blood's acidity, or pH. Carbon dioxide, when dissolved in the blood, becomes acidic. By changing how fast or deep you breathe, your respiratory system can literally change the chemistry of your blood in seconds, keeping it in the very narrow range required for your survival. Furthermore, the system is a magnificent filter. Every day, you breathe in thousands of liters of air, and that air is filled with dust, pollen, and bacteria. Your respiratory tract is lined with a specialized mucociliary escalator. This is a layer of sticky mucus that traps invaders in tiny hair-like structures called cilia that beat rhythmically to move that mucus up and away from your lungs. It is a constant sweeping motion, like a tireless janitor cleaning the halls of a great estate while the master sleeps. Think of the sheer elegance of this. While you are resting, your body is not only fueling itself, but also meticulously cleaning itself and balancing its own internal chemistry. It is a level of care and detail that is truly a wonder of the natural world. Real-world relevance and synthesis, connecting the dots. You might wonder how this academic knowledge applies to your life outside of a textbook. Well, consider the act of speaking. Every word I am saying to you right now is a secondary gift of the respiratory system. We have evolved to use the air we are already exhaling to vibrate our vocal cords, and creating the sounds of human language. Without the precise control of pulmonary ventilation, Music, laughter, and conversation would be impossible. Consider also the feeling of being out of breath when you run. That isn't just your lungs being tired, it is a sophisticated feedback loop. Your brain senses a rise in carbon dioxide, the smoke from your muscles fires, and it commands your respiratory muscles to work harder to clear it out. This system is so finely tuned that it can increase its output by 20 times the resting rate during intense exercise. So you see, this isn't just a theory in a book. It's the principle that explains why you sigh when you're relieved, why you pant when you're hot, and why your breath slows down so beautifully as you prepare for sleep. It is the fundamental rhythm of your existence. Don't worry about memorizing every term I've mentioned tonight. Just let the logic of it wash over you. The system is designed for your success. It is designed to keep the fire of life burning steadily, without you ever having to lift a finger to manage it. We have spent our time tonight looking at the big picture, the philosophy and the primary goals of the respiratory system. We've seen the 4 stages of respiration and understood that this system is the bridge between the atmosphere and your cells. It is a protector, a balancer, and a provider. Having now grasped the purpose and the why, we are perfectly prepared to appreciate the where. It's much easier to understand the shape of a building once you know what people do inside of it. So, let's hold that thought here, a complete piece of the puzzle. When we return in our next lesson, we will begin our physical tour of the system, starting at the very beginning, where the air first makes contact with you. We will explore the specialized chambers of the nose and the throat and see how they prepare the air for its long journey down. For now, just focus on the feeling of your own breath. Notice how effortless it is. Notice the coolness as you breathe in and the warmth as you breathe out. You are in good hands, your own. Sleep deeply, and I will see you in the next lesson. Next, Lesson 2, Anatomy of the Upper Respiratory Tract. As we continue our journey together, I want you to take a moment to notice the air as it passes through your nostrils. Perhaps it feels a bit cool against the skin, or perhaps you can catch the faint, lingering scent of lavender or the crisp night air. This sensation is your first introduction to the upper respiratory tract. It is the gateway, the grand foyer of your body's internal cathedral. While we often think of the lungs as the stars of the show, the air would be far too harsh, too dry, and too dirty for the delicate tissues deep inside you if it weren't for the sophisticated processing plant located right behind your face. Tonight we are going to explore this lobby of the system, the nose, the pharynx, and the larynx, and discover how they act as the ultimate concierge for every breath you take. In our last session, we looked at the big picture, the 4 stages of respiration, and the essential why behind our breathing. Tonight, we take the next natural step in our learning journey and explore the anatomy of the upper respiratory tract. We are moving from the abstract concept of gas exchange to the physical reality of the structures that handle the air first. We will see how the nose is much more than a feature on your face. It is a climate control center and a sophisticated filter. We will follow the path of the air as it enters the pharynx, a versatile crossroads where the paths of food and air meet. And finally, we will arrive at the larynx. The larynx is a fascinating gatekeeper, ensuring that the breath of life goes to the lungs while the nourishment of food goes to the stomach, all while providing us with the incredible gift of speech. Think of this as the preparation phase of respiration, where the atmosphere is refined and invited in. The journey begins with the nose and the nasal cavity. When you inhale, air typically enters through the external nares, which most of us simply call the nostrils. Immediately, the air enters the vestibule, an area lined with coarse hairs called vibrissae. These hairs are your body's first line of defense, acting like a picket fence to trap large particles of dust or insects before they can travel any further. But the true engineering marvel lies deeper, within the nasal cavity itself. Inside this cavity, the space is divided by the nasal septum and characterized by three uneven, scroll-like bones called the nasal conchae. These bones, the superior, middle, and inferior conchae, protrude from the lateral walls like curved shelves. Their purpose is not to make the path easy, but to make it turbulent. As the air hits these shelves, it is forced into a series of swirls and eddies. Imagine a calm stream suddenly hitting a series of smooth river stones. The water splashes and churns, ensuring every drop touches the stones. In your nose, this turbulence ensures that nearly all the air comes into contact with the warm, moist mucous membrane lining the cavity. As the air swirls, it is warmed by the dense network of capillaries just beneath the surface and humidified by the mucus secreted by specialized goblet cells. This is vital because the lungs are tropical environments. They require air that is nearly 100% humidified and exactly body temperature. By the time the air leaves your nasal cavity, it has been cleaned, moistened, and heated. From the nasal cavity, the air moves into the pharynx, or what we commonly call the throat. The pharynx is a muscular tube that serves as a common hallway for both the respiratory and digestive systems. It is divided into three distinct regions. The uppermost part is the nasopharynx, which lies behind the nasal cavity and serves only as an air passage. Below that is the oropharynx, located behind the oral cavity, where both swallowed food and inhaled air pass through. Finally, we reach the laryngopharynx, the point where the path eventually diverges. At the base of the laryngopharynx sits the larynx, or the voice box. The larynx is a complex structure made of 9 pieces of cartilage, the most prominent being the thyroid cartilage, which you might know as the Adam's apple. The larynx has 2 primary jobs. First, it acts as a switching station. During swallowing, the larynx moves upward, and a flexible, leaf-shaped flap of cartilage called the epiglottis folds down to cover the opening of the airway. This is a brilliant mechanical solution to a dangerous problem. It ensures that your dinner goes down the esophagus to the stomach rather than into your windpipe. Its second job, which we will touch on shortly, is the production of sound. While we've discussed the physical structures, the how of the upper respiratory tract is deeply tied to its microscopic lining. Most of the tract is covered in a specialized tissue called pseudostratified ciliated columnar epithelium. That is a long name for a very simple and beautiful mechanism. Every one of these cells is topped with tiny hair-like structures called cilia. These cilia beat in a synchronized rhythmic wave, about 10 to 12 times per second. Above the cilia sits a layer of sticky mucus. This mucus is the flypaper of the respiratory system, catching microscopic dust, pollen, and bacteria that the nose hairs missed. The cilia then act like a conveyor belt, or what scientists call the mucociliary escalator, slowly moving that dirty mucus upward and away from the lungs toward the pharynx. Once it reaches the throat, you unconsciously swallow it, and the stomach acid neutralizes any trapped pathogens. It is a tireless and 24-hour cleaning service that protects your lower respiratory system from infection and irritation. Historically, our understanding of the larynx and vocal production was greatly advanced by the invention of the laryngoscope in the mid-19th century by a singing teacher named Manuel Garcia. By using a small mirror and sunlight, he was the first to observe the living vocal folds in action. These folds are actually two pearly white ribbons of elastic ligament. When you aren't speaking, they stay wide apart to let air pass freely. But when you want to make a sound, muscles pull them tight and narrow the opening. As air is pushed up from the lungs, the folds vibrate, creating sound waves. The pitch of your voice is determined by how much tension is on those folds, much like the strings on a guitar or a violin. And it is a reminder that your respiratory system isn't just for survival. It is the instrument of your soul's expression. Furthermore, the upper respiratory tract is intimately connected to your sinuses, 4 pairs of air-filled cavities in the bones of your skull. While they are often the source of sinus headaches, their biological purpose is quite elegant. They lighten the weight of the skull, and like the nasal cavity, they are lined with mucous membranes that help warm and moisten air. They also act as resonance chambers, giving your voice its unique, full-bodied sound. If you've ever noticed how your voice sounds flat or nasal when you have a cold, it's because those chambers are filled with fluid, losing their ability to vibrate with your voice. So you see, this isn't just a collection of tubes and cartilage in a textbook. It is a living, breathing laboratory that is constantly adjusting to your environment. When you walk into a cold winter day, the blood vessels in your nose dilate, bringing in more warm blood to heat the freezing air. This is why your nose might get red or start to run. Your body is actually over-humidifying the air to protect your lungs from the shock of the cold. This system also explains why we are told to breathe through our noses during exercise or when we are trying to calm down. Mouth breathing bypasses the turbulence of the conchae and the filtration of the nasal hairs. It delivers air to the lungs that is drier and cooler, which can sometimes trigger coughing or irritation. By using your nose, you are utilizing the full concierge service of the upper respiratory tract, ensuring that every breath is of the highest quality before it reaches the delicate tissues below. Even the simple act of clearing your throat is a synthesis of these parts working together. It is a forceful blast of air designed to dislodge mucus that the ciliary escalator has brought to the switching station of the pharynx. Every sniffle, every hum, and every silent breath is a testament to the coordination of these structures. They are the guardians of the gate, working in perfect harmony to ensure the air is prepared for the deeper journey it is about to take. Take a moment to let that idea find its place in your mind. You can picture the air now swirling through those curved conchae, being warmed and cleaned, and passing safely over the gate of the epiglottis. It is a peaceful and orderly process that is happening right now as you listen to my voice. We have now grasped the structure of the gateway, and we are perfectly prepared to appreciate the journey further down. We've seen how the air is prepared in the lobby, but where does it go once it passes the larynx? Our next lesson will take us into the deep interior, following the air into the sturdy windpipe and the branching tree-like paths of the chest. Let's hold that thought here, a complete piece of the puzzle. When we return, we will begin our study of the anatomy of the lower respiratory tract, where the air finally reaches the threshold of the blood itself. For now, just rest in the knowledge that your body is expertly managing these gates. Your breath is clean, your airway is clear, and you are safe. Sleep well. And I will be here when you are ready to continue. Lesson 3. Anatomy of the lower respiratory tract. As we move deeper into our study, I want you to imagine the air has now passed the security checkpoint of the upper respiratory tract. It has been warmed, it has been humidified, and it has been filtered of the larger debris of the outside world. It is now ready to descend into the deep, protected interior of your chest. If the upper respiratory tract was the lobby of a grand building, we are now entering the main corridors and the specialized inner chambers. This is the lower respiratory tract, a world of branching pathways that look less like a machine and more like an inverted tree. In fact, we often call this the bronchial tree. Tonight, we will follow the air through the sturdy trachea, into the bifurcating bronchi, and finally into the lush, spongy lobes of the lungs themselves. And in our previous session, we explored the gates and the guards of the upper respiratory tract. Tonight, we take the next natural step in our learning journey as we explore the anatomy of the lower respiratory tract. This is where the architecture of your body undergoes a fascinating transformation. We begin with a single, sturdy trunk, the trachea, and watch as it divides and subdivides into smaller and smaller branches until it reaches a microscopic scale. We will examine why the trachea is built with its peculiar C-shaped rings, why your two lungs aren't actually identical twins, and how the entire structure is designed to maximize the surface area for life-giving oxygen. As we descend together, I want you to visualize the strength and the delicacy of these structures, working in perfect concert to move the atmosphere into the very core of your being. The journey into the lower respiratory tract begins immediately below the larynx, with a structure called the trachea, or more commonly, the windpipe. The trachea is a remarkable piece of biological engineering. It is a tube about 4 to 5 inches long, and if you were to reach up and gently touch the base of your neck, you might feel the firm, ridged texture of its walls. These ridges are actually 16 to 20 C-shaped rings of hyaline cartilage. I want you to think about why those rings are C-shaped rather than complete circles. The open part of the C faces toward your back, right against your esophagus. This is a brilliant bit of space-saving design. When you swallow a large bite of food, your esophagus needs to expand to let it pass. Because the trachea's rings are open at the back, the esophagus can bulge slightly into the trachea's space, ensuring your food moves smoothly towards your stomach without getting stuck. Meanwhile, the firm cartilage of the C ensures that the airway stays open at all times, preventing it from collapsing like a wet straw when you take a deep breath. At its base, the trachea reaches a point called the carina. This is a sensitive fork in the road, where the trachea splits into two primary bronchi, one heading to the right lung and one to the left. The right primary bronchus is slightly wider, shorter, and more vertical than the left. This is a small detail, but a significant one in a university clinic. If someone accidentally inhales a foreign object, and it is statistically more likely to end up in the right lung because the path is more of a straight shot. Once these bronchi enter the lungs, the branching truly begins. The primary bronchi divide into secondary or lobar bronchi, one for each lobe of the lungs. The right lung, being slightly larger, has 3 lobes, and therefore 3 secondary bronchi. The left lung, which graciously makes room for the heart, has only 2. These then divide into tertiary bronchi, which divide into even smaller tubes called bronchioles. As we travel further down this tree, the anatomy changes. The sturdy cartilage rings of the trachea gradually disappear, replaced by small plates of cartilage, and eventually by a layer of smooth muscle. By the time we reach the smallest bronchioles, there is no cartilage at all. This allows the body to use that smooth muscle to dilate or constrict the airways, precisely controlling the flow of air. Finally, at the very tips of these microscopic twigs, we find the terminal bronchioles, which lead us into the respiratory zone, the end of the line for the air's journey. While the tubes are the pathways, the lungs are the destination. They are large cone-shaped organs that occupy most of the thoracic cavity. It is a common misconception to think of the lungs as hollow balloons. In reality, if you were to touch a healthy lung, it would feel much more like a fine-grained, airy sponge. This sponginess comes from the millions of tiny air sacs and the elastic connective tissue that holds them all together. The lungs are divided by deep grooves called fissures. The right lung has both a horizontal and an oblique fissure, creating the superior, middle, and inferior lobes. The left lung has only an oblique fissure, creating the superior and inferior lobes. On the medial surface of the left lung, there is a distinct indentation called the cardiac notch. This is where the apex of your heart nestles comfortably against the lung tissue. This intimate proximity is no accident. The heart and lungs are the most dedicated partners in your body, and their physical closeness reflects their functional interdependence. The entire surface of the lungs and the inside of your chest wall is covered by a very special serous membrane called the pleura. The pleura is composed of 2 layers: the visceral pleura, which sits directly on the lung tissue, and the parietal pleura, which lines the chest cavity. Between them is a microscopic space called the pleural cavity, filled with a thin film of pleural fluid. This fluid is the lubricant of your breath. It allows the lungs to slide effortlessly against the chest wall as you breathe, reducing friction to nearly 0. But it does something even more important. It creates surface tension that glues the lungs to the chest wall. Think of 2 wet sheets of glass pressed together. They can slide against each other easily, but they are incredibly difficult to pull apart. This ensures that when your chest expands, your lungs must expand with it. This vacuum-like seal is what allows you to breathe without conscious effort. Historically, our understanding of this branching tree was revolutionized by the development of the microscope. Early anatomists could see the trachea and the large bronchi, but they couldn't fathom how such a small space could process so much air. It was only when we could see the microscopic level, the leaves of the tree, that we realized the lung's true genius. By branching so many times, The body creates a massive surface area in a very small volume. If you were to flatten out all the pathways and sacs in your lungs, they would cover nearly 750 square feet. It is a vast internal landscape hidden within the quiet confines of your ribs. So, why does this complex branching matter in your daily life? Consider the sensation of a chest cold or bronchitis. That is an inflammation of these very tubes we've been discussing. When the bronchi or bronchioles become inflamed, the smooth muscle can spasm, and the lining can produce excess mucus, narrowing the path for the air. This is why you feel that tightness in your chest. Your body is struggling to move air through a tree that has become congested. Consider also the phenomenon of second wind, or the feeling of your lungs opening up during a walk. This is the smooth muscle in your bronchioles responding to signals from your nervous system. When you need more air, your body releases chemicals that tell that smooth muscle to relax, widening the twigs of the tree to let more air flow through. It is a dynamic living system that adjusts its own diameter second by second to meet your needs. Even as you lie here now preparing for sleep, your lower respiratory tract is adjusting. As your heart rate slows and your demand for oxygen decreases, the tree slightly constricts its outer branches. The pleural fluid is silently ensuring that every expansion of your ribs is met with a perfectly mirrored expansion of your lungs. This isn't just a theory in a book. It is the physical reality of how you are staying alive in this very moment. You see, the lower respiratory tract is a bridge between the physical world of air and the microscopic world of the blood. It is a masterpiece of plumbing, structural support, and fluid dynamics. By understanding the sturdy rings of the trachea and the delicate branching of the bronchioles, you can begin to see how much care your body takes to protect the air on its way to its final destination. Take a moment to let that logic wash over you. Visualize the sturdy trachea, the straight shot to the right lung, and the soft, spongy lobes resting behind your ribs. It is a harmonious piece of the puzzle. We have now grasped the structure of the pathways, the hallways, and corridors of the system. But as we know, a hallway eventually leads to a room. Our next lesson will take us to the very end of those branching twigs, to the tiny grape-like clusters where the air finally meets the blood. This is where the most important work of the entire system happens. So, when we return, we will focus our attention on the smallest scale imaginable, the structure and function of the alveoli. For now, just focus on the rhythmic rise and fall of your chest. Trust in the sturdy cartilage and the smooth muscle. Your bronchial tree is at rest, and the air is moving exactly where it needs to go. Sleep deeply, and I will be here to guide you further when you wake. Lesson 4. The structure and function of the alveoli. Tonight, we arrive at the destination. Every structure we have studied so far, the nasal conchae that warmed the air, the epiglottis that guarded the path, the sturdy rings of the trachea, and the sprawling branches of the bronchial tree, exists for this single microscopic goal. We have reached the very edges of the respiratory map. If you were to follow a single molecule of oxygen on its long journey from the night air, past your lips, and down the winding tunnels of your chest, it would finally come to rest here, in a tiny shimmering sac called an alveolus. This is the business end of the system. It is here that the external world finally shakes hands with your internal world. It is a place of incredible thinness, profound fragility, and life-sustaining power. In our previous session, we followed the air through the grand corridors of the lower respiratory tract, marveling at the branching architecture of the lungs. Tonight, we zoom in even further, past the limits of what the naked eye can see, to explore the structure and function of the alveoli. This is the next natural step in our learning journey, because it represents the transition from transport to exchange. We are going to look at the three specialized cell types that call these air sacs home and understand the miraculous respiratory membrane, a barrier so thin that it allows gases to pass through while keeping your blood where it belongs. We will also discover the secret sauce of the lungs, a substance called surfactant, which prevents these tiny bubbles from collapsing under the weight of life. Think of this as the microscopic frontier, where biology and physics meet to perform the ultimate act of alchemy, turning breath into life. To understand the alveoli, we must first appreciate their numbers. Your lungs contain approximately 300 to 400 million of these tiny air sacs. If you were to look at them through a microscope, they would look like a cluster of grapes hanging at the end of a bronchiole. Each individual grape is an alveolus. Collectively, they provide a massive surface area, which is necessary because the exchange of gases is a game of probability. The more surface area you have, the more likely an oxygen molecule is to find its way into your blood. The wall of an alveolus is a masterpiece of minimalist design. It is primarily composed of type 1 alveolar cells. These are simple, squamous epithelial cells, which is a fancy way of saying they are incredibly flat and thin like tiny paving stones. They are so thin that they barely have a third dimension. This thinness is the key to their function, because oxygen and carbon dioxide move by simple diffusion, drifting from where there is a lot of them to where there is a little. They need a path that is as short as possible. Wrapped tightly around these type 1 cells is a dense cobweb of pulmonary capillaries. These are the smallest blood vessels in your body, and they are so narrow that red blood cells must pass through them in single file, like commuters moving through a turnstile. The space where the wall of the alveolus meets the wall of the capillary is what we call the respiratory membrane. The respiratory membrane is the most important boundary in your body. It consists of the alveolar epithelium, the fused basement membrane, and the capillary endothelium. Despite having 3 layers, it is only about 0.5 micrometers thick. To put that into perspective, it is about 1/50th the thickness of a sheet of tissue paper. This extreme thinness allows oxygen to hop from the air into the blood, and carbon dioxide to hop from the blood into the air in a fraction of a second. However, having millions of tiny wet bubbles inside your chest presents a physical problem: surface tension. Water molecules are naturally attracted to one another, and in a tiny sphere like an alveolus, that attraction wants to pull the walls inward, causing the bubble to collapse and stick shut. This is where the type 2 alveolar cells come in. These cells are fewer in number and more cuboidal in shape. Their job is to produce and secrete a complex mixture of lipids and proteins called surfactant. Surfactant acts like a microscopic detergent. It gets in between the water molecules and breaks their attraction to one another significantly reducing the surface tension. Without surfactant, your lungs would be like a wet plastic bag that has been pressed flat. It would take an immense and exhausting amount of force to peel them open with every breath. Thanks to these type 2 cells, your alveoli remain open and flexible, even when you exhale and they reach their smallest size. While the type 1 and type 2 cells handle the structure and the physics, there is a third resident of the alveoli that handles the defense. The alveolar macrophages, might often called dust cells. Even with the filters of the nose and the mucociliary escalator of the bronchi, some microscopic invaders, bacteria, soot, or fine dust, manage to reach the very bottom of the lungs. Because the alveoli are so delicate, they cannot be lined with the sticky mucus or the beating cilia we find in the larger airways. That would make the respiratory membrane too thick for gas exchange. Instead, these macrophages act as a mobile security force. They crawl along the inner surfaces of the alveoli like microscopic vacuum cleaners, engulfing and digesting any foreign particles they find. Once they have cleaned up, they are eventually swept up into the bronchioles where the escalator can take them away, or they simply dissolve. Their job done. It is a silent, microscopic war being fought for your health with every breath you take. Historically, our understanding of surfactant is a relatively recent chapter in medical history. In the mid-20th century, doctors struggled to understand why some premature infants, despite having seemingly healthy lungs, would die of respiratory distress shortly after birth. It was eventually discovered that the type 2 cells don't begin producing surfactant until very late in pregnancy. Without this secret sauce, the infant's lungs were simply too sticky to stay open. This discovery led to one of the great triumphs of modern medicine, the development of synthetic surfactant, which is now routinely given to premature babies, saving countless lives. Another layer of this story is the sheer efficiency of the blood's transit. A red blood cell spends only about 0.75 seconds passing through the pulmonary capillaries. In that less than a second window, it must unload its carbon dioxide and fill its hemoglobin seats with oxygen. Remarkably, under normal resting conditions, the blood becomes fully saturated with oxygen in just 0.25 seconds, 1/3 of the time available. This means your body has a safety margin of 300%. Even if your blood moves faster during exercise, or if the membrane becomes slightly thickened, you have time to spare. Your body is built for resilience. So how does this microscopic world show up in your life? Think of the last time you had a deep chest-rattling cough. In conditions like pneumonia, the alveoli can become inflamed and fill with fluid or pus. When this happens, the dry environment of the alveoli is lost. Suddenly, that 0.5 micrometer respiratory membrane is separated from the air by a pool of liquid. Because oxygen doesn't move through water as easily as it moves through air, the diffusion process slows down or stops. This is why pneumonia feels so exhausting. Your body is working twice as hard to get half the oxygen. Consider also the long-term impact of irritants like cigarette smoke or severe air pollution. These can damage the walls of the alveoli, causing them to lose their elasticity and eventually rupture. When the walls between grapes break down, you end up with fewer, larger air sacs. This is the hallmark of emphysema. While it might sound like having more space is good, It actually reduces the total surface area. It's like taking a beautifully detailed book with 1,000 pages and gluing them all together into 10 thick chunks. And you lose the information, the surface area, where the exchange happens. Even as you lie here now, these millions of sacs are performing their delicate dance. Every time you inhale, they inflate slightly, and the surfactant spreads out to keep them stable. Every time you exhale, they shrink, and the surfactant becomes more concentrated to prevent them from sticking. It is a constant rhythmic pulsation of life. You don't have to monitor the surface tension of your 400 million sacs. Your type 2 cells are on it. You don't have to check for dust in the deep interior. Your macrophages are patrolling the halls. The alveoli are the ultimate testament to the idea that the most important things in life are often the ones we cannot see. They are the quiet, microscopic engine of your existence. By understanding their structure, you aren't just learning anatomy, you are learning about the incredible fragility and strength that allows you to exist in this world. Take a moment to let that idea rest in your thoughts. Visualize that shimmering microscopic forest of air sacs, protected by surfactant and guarded by macrophages. It is a complete and vital piece of our puzzle. We have now reached the end of the physical path. We have followed the air from the nose all the way to the respiratory membrane. But we haven't yet discussed the how of the movement. We know where the air goes, but what force actually pulls it in? What tells the chest to expand and the lungs to follow? Our next lesson will step back from the microscope to look at the mechanics of the whole body. We will explore the physics of pressure and volume, and the muscles that act as the bellows for your life. So, when we return, we will begin our study of the mechanics of pulmonary ventilation. For now, just let your breathing be. Trust in the thinness of your membranes and the efficiency of your surfactant. You are breathing perfectly. Sleep deeply. And I will be here when we continue our journey. Lesson 5, Mechanics of Pulmonary Ventilation. As you lie there, perhaps noticing the gentle rhythmic rise and fall of your chest, I want to ask you a question that might seem simple at first. Why does the air move? When you inhale, what force is pulling that invisible mixture of nitrogen and oxygen into your body? It isn't as if the atmosphere is being shoved down your throat by some external hand. Instead, your body is performing a sophisticated dance with the laws of physics. It is creating an invitation. This lesson is about that invitation, the mechanics of pulmonary ventilation. We are moving from the where of the respiratory system to the how. We are going to look at the muscles, the membranes, and a fundamental law of physics that governs every breath you will ever take. In our last session, we reached the microscopic frontier, the alveoli, where the air finally meets the blood. Tonight, we take the next natural step in our learning journey by zooming out to look at the body as a whole. We are going to explore the mechanics of pulmonary ventilation. This is the study of how we move air in and out of the lungs. To do this, we have to look at the body as a bellows. We will discuss the diaphragm, that great sheet of muscle that serves as the floor of your chest, and the intercostal muscles that act as the scaffolding for your ribs. We will also introduce an old friend from the world of physics, Boyle's law. This law is the secret code that explains how changing the size of a container changes the pressure inside it. By the end of this lesson, you'll see that breathing isn't something you do to the air. It's something you do with the space around the air. To understand breathing, we must first understand the relationship between pressure and volume. Imagine you have a sealed container, like a syringe or a piston. Inside that container are gas molecules, bouncing around like tiny energetic rubber balls. If you shrink the container but keep the number of balls the same, they will hit the walls more often. This increase in hits is what we call an increase in pressure. Conversely, if you make the container larger, the balls have more room to roam, they hit the walls less frequently, and the pressure drops. This is Boyle's law. Pressure and volume are inversely related. If volume goes up, pressure goes down. Your chest cavity is that container. It is a sealed box bounded by your ribs, your spine, and the diaphragm. For air to enter your lungs, the pressure inside your chest must be lower than the pressure of the atmosphere outside. Since you cannot easily change the pressure of the entire world, your body changes the volume of your chest instead. When you begin to inhale, your brain sends a signal to the diaphragm. This muscle is shaped like a dome or an umbrella, tucked up under your lungs. When it receives the signal, it contracts and flattens out, moving downward toward your abdomen. At the same time, your external intercostal muscles, the muscles between your ribs, contract, pulling your rib cage up and out, much like the handle of a bucket being lifted. These two movements significantly increase the volume of your thoracic cavity. And what does Boyle's law tell us happens when volume increases? The pressure inside drops. Specifically, the intrapulmonary pressure, the pressure inside the alveoli, falls just slightly below the atmospheric pressure. This creates a vacuum. The air from the outside world doesn't need to be pushed. It simply rushes in to fill that low pressure space until the pressures are equalized. This is inspiration. Expiration, the act of breathing out, is usually a more passive process when you are at rest. Think of it like a rubber band that has been stretched. When the diaphragm and intercostal muscles relax, the natural elasticity of the lung tissue and the chest wall causes them to recoil. The diaphragm moves back up into its dome shape, and the ribs drop down and in. This decreases the volume of the chest cavity. As the volume shrinks, the pressure inside the lungs rises above the atmospheric pressure, and the air is squeezed out. It is a beautiful, self-regulating cycle. Your body creates a space, and the universe fills it. Then, your body relaxes that space, and the universe accepts the air back. It is a conversation with the atmosphere that never ends. While the movement of the muscles is the engine of breathing, there is a hidden layer of physics that ensures the lungs actually follow the chest wall. We touched on the pleura in an earlier lesson, but now we must see it in action. The parietal pleura is attached to the chest wall, and the visceral pleura is attached to the lung itself. Between them is a tiny amount of pleural fluid. This fluid creates a very low pressure, known as intrapleural pressure. This pressure is always negative relative to the air inside the lungs. Think of it as a constant suction that keeps the lungs stuck to the inside of the ribs. And if you've ever tried to pull apart two wet microscope slides, you know exactly how strong this suction can be. They slide easily, but they won't pull apart. Because of this negative pressure, whenever the chest wall expands, the lungs must expand with it. If this vacuum were ever broken, by a wound to the chest, for example, the lung would naturally shrivel up like a deflated balloon because its own elasticity would no longer be countered by that pleural suction. Historically, our understanding of these mechanics was a slow realization. Early physicians like Galen in the 2nd century noticed the diaphragm's movement, but didn't quite grasp the role of air pressure. It wasn't until the 17th century, when scientists like Robert Boyle began experimenting with vacuum pumps and air pressure, that we finally understood that we are living at the bottom of a sea of air. We realize that we don't suck air in. We simply create the conditions for the atmosphere to push its way in. There is also the concept of resistance to consider. Not all breaths are created equal. The ease with which the lungs can expand is called compliance. Healthy lungs are highly compliant. They are like a brand new, high-quality balloon that is easy to blow up. This compliance comes from the elastic fibers in the lung tissue and the presence of surfactant, which we discussed in the last lesson. If the lungs become scarred or if surfactant is missing, compliance drops. Breathing then becomes a chore, an exhausting labor, rather than the effortless rhythm you are experiencing now. You can feel these mechanics in action throughout your day. Think of the last time you were startled and took a sharp intake of breath. That was a rapid, forceful contraction of your diaphragm and external intercostals, creating a sudden deep vacuum that the air rushed to fill. Or consider what happens when you blow out a candle. This is forced expiration. Unlike resting expiration, which is passive, this requires your internal intercostal muscles and your abdominal muscles to contract forcefully. They pull the ribs down even further and push the abdominal organs up against the diaphragm, shrinking the chest volume much faster and more dramatically than usual. This creates a high-pressure blast of air. Even the way you are positioned right now affects these mechanics. If you were hunched over, your ribs wouldn't be able to move up and out as easily, and your abdominal organs would press against your diaphragm, making it harder for it to move down. By lying back and relaxing, you are giving your respiratory muscles the best possible mechanical advantage. You are making it as easy as possible for Boyle's law to do its work. So you see, this isn't just a theory in a book. It's the principle that explains why a punctured lung collapses, why we use iron lungs for people who can't move their own muscles, and why deep breathing is so effective for relaxation. When you take a deep, slow breath, you are consciously maximizing the volume of your chest, creating the largest possible invitation for the air to enter. You are literally expanding your space to accommodate more of the world. Take a moment to let that idea find its place and try to feel the very slight tension as you inhale. That is your muscles creating the vacuum. Then feel the complete release as you exhale. That is the natural elasticity of your body returning to its resting state. It is a complete piece of the puzzle. We have now grasped the mechanics, the bellows of the system. We know how we get the air into the sacs. But once the air is in the alveoli and the blood is in the capillaries, we have to look closer at the silent swap. How exactly do oxygen and carbon dioxide cross that thin membrane? It isn't just about big pressures in the chest anymore. It's about the partial pressures of the gases themselves. So, let's hold that thought here. When we return, we will dive back into the chemistry and the physics of the exchange itself. we will begin our study of the gas laws and gas exchange. For now, just let the rhythm continue. Your diaphragm knows exactly what to do. You are breathing in harmony with the laws of the universe. Sleep well, and I will be here to continue our journey when you are ready. Lesson 6. Gas laws and gas exchange. We have reached a pivotal moment in our journey. Up until now, we have focused on the physical movement of the air, the plumbing of the tubes, and the bellows of the chest. But now, the air is sitting quietly in the alveoli, and the blood is rushing through the capillaries just a fraction of a millimeter away. There are no pumps here, no moving parts, and no active gates to usher the gases across. Instead, we enter the realm of the silent swap. This is where the laws of the universe take over entirely. If the mechanics of breathing were a dance of muscles, gas exchange is a dance of molecules. Tonight, we are going to look at the invisible forces that govern how oxygen decides to enter your blood and how carbon dioxide knows it is time to leave. In our previous session, we used Boyle's law to understand how the movement of your diaphragm creates the pressure changes that pull air into your lungs. Tonight, we take the next natural step in our learning journey by exploring gas laws and gas exchange. We are going to move beyond total air pressure and look at the individual pressures of the gases that make up our atmosphere. We will introduce two fundamental principles: Dalton's law, which explains why each gas acts as if it is the only one in the room, and Henry's law, which tells us how these gases dissolve into the liquid of our blood. We will follow the path of a single oxygen molecule as it crosses the respiratory membrane, and we'll see why the system is so beautifully efficient that it works even when you are fast asleep. Think of this as the chemistry of life in its purest form, a silent, effortless balancing act that happens millions of times every day. To understand how gases move between the air and the blood, we have to look at the atmosphere differently. The air around you is a mixture, mostly nitrogen, a good portion of oxygen, and a tiny bit of carbon dioxide and water vapor. Dalton's law of partial pressures tells us that in a mixture of gases, the total pressure is simply the sum of the pressures exerted by each individual gas. We call the pressure of a single gas its partial pressure. Imagine a crowded room filled with people wearing red hats and blue hats. Dalton's law suggests that if you want to know how much the red hat people are pushing against the walls, you only need to count the red hats. The blue hats don't interfere with the red hat's pressure. In your lungs, in the partial pressure of oxygen, which we write as PO2, is the only thing that determines how much oxygen wants to move. It doesn't matter how much nitrogen is there, the oxygen acts on its own. Gas exchange is driven entirely by a process called diffusion. Diffusion is the natural passive movement of molecules from an area where they are highly concentrated to an area where they are less concentrated. It is like a drop of ink spreading in a glass of water. It doesn't need to be stirred. The molecules simply want to find balance. In the alveoli, the PO2 is high because you have just inhaled fresh air. In the blood arriving at the lungs, the PO2 is low because your body has used that oxygen up. Because of this pressure gradient, oxygen naturally tumbles across the respiratory membrane and into the blood. At the same time, the partial pressure of carbon dioxide, PCO2, is much higher in the blood than in the air. So CO2 tumbles in the opposite direction, leaving the blood and entering the alveoli to be exhaled. However, there is a catch. The gases aren't just moving from air to air, they have to dissolve into the liquid of your blood. This is where Henry's law comes in. It states that the amount of gas that will dissolve in a liquid is proportional to its partial pressure and its solubility. Some gases like being in water more than others. Carbon dioxide, for instance, is about 20 times more soluble in blood than oxygen is. This is why, even though the pressure gradient for CO2 is much smaller than it is for oxygen, CO2 can still move just as quickly out of the blood. It is simply much better at swimming through the liquid. The efficiency of this exchange is one of the most remarkable features of human physiology. As we discussed in an earlier lesson, the respiratory membrane is incredibly thin. But there are other factors that determine how well this silent swap happens. One of the most important is what we call ventilation-perfusion coupling. In a perfect world, every air sac would be perfectly ventilated with air, and every capillary would be perfectly perfused with blood. But the body is dynamic. Some alveoli might be a bit squashed, or some capillaries might be slightly constricted. Your body is smart enough to match them up. If a certain group of alveoli isn't getting much air, the body actually constricts the blood vessels going to those sacs. Why send blood to a place where there is no oxygen to catch? Instead, it redirects that blood to the parts of the lung that are currently well ventilated. It is a real-time supply and demand system that ensures no effort is wasted. Historically, the discovery of these laws was a triumph of 19th century chemistry. John Dalton, a self-taught English scientist, formulated his law of partial pressures in 1801 while studying the properties of the atmosphere. He was fascinated by how gases could coexist without reacting. A few decades later, William Henry, a friend of Dalton's, expanded on this by looking at how gases interact with liquids. Together, their work provided the blueprint that allows modern doctors to understand everything from how to set a ventilator in a hospital to how to treat a diver with the bends. Speaking of diving, Henry's law explains a fascinating and dangerous phenomenon. When a diver goes deep underwater, the high pressure of the water pushes more nitrogen into their blood than usual. If the diver swims to the surface too quickly, the pressure drops suddenly, and that nitrogen can no longer stay dissolved. It turns back into gas, forming bubbles in the blood, much like the bubbles that form when you quickly open a pressurized bottle of soda. This is decompression sickness. It shows us that we are always at the mercy of these gas laws. Our bodies are perfectly calibrated for the pressure at the surface of the earth. You can see the importance of these gradients in how we treat people who are struggling to breathe. If a person has damaged lungs and their diffusion is poor, and we often give them supplemental oxygen. By increasing the concentration of oxygen in the air they breathe, we are artificially raising the PO2 in their alveoli. This creates a much steeper hill for the oxygen to roll down, forcing more of it across even a damaged membrane. We are using Dalton's law to override a biological hurdle. Think also about why you might feel lightheaded if you breathe too fast, what we call hyperventilation. When you breathe rapidly, you blow off too much carbon dioxide. This lowers the PCO2 in your blood far below its normal level. Because CO2 helps regulate the diameter of blood vessels in your brain, This sudden drop causes those vessels to constrict. You are literally changing the chemistry of your brain by altering the gas pressures in your lungs. Even as you are resting now, your body is maintaining these gradients with exquisite precision. With every quiet inhale, you are refreshing the red hats in the room, keeping the oxygen pressure high so it continues to flow into your blood. With every quiet exhale, you are clearing out the blue hats, keeping the CO2 pressure low so your blood can stay clean. Don't worry about the math or the specific numbers of the pressures. Just try to visualize the elegance of it. It is a system that requires no conscious thought, no energy-consuming pumps, and no complex machinery. It is simply the universe seeking balance through the thin, delicate tissues of your lungs. You are participating in a fundamental physical process that has been part of life on Earth since the first lungs evolved. Take a moment to let that idea find its place. Visualize the oxygen molecules hopping across that tiny gap into the blood, and the carbon dioxide hopping back out. It is a complete, beautiful piece of the puzzle. We have now grasped the silent swap. We know how the gases get into the bloodstream. But once the oxygen is in the blood, it has a long way to go. It has to travel from your chest all the way to your brain, your heart, and your furthest fingertips. The blood is mostly water. And as we learned from Henry's law, oxygen doesn't dissolve very well in water. It needs a specialized transport vehicle to carry it in the large amounts we need. So, let's hold that thought here. When we return, we will meet the most important molecule in your blood, hemoglobin. We will begin our study of the transport of respiratory gases for now, and just focus on the effortless nature of your breath. Your gases are diffusing perfectly. Your blood is being refreshed. You are in perfect balance with the air around you. Sleep well, and I will be here to continue our journey when you are ready. Lesson 7. Transport of respiratory gases. We have reached a magnificent turning point in our story. The oxygen has successfully crossed the microscopic border of the respiratory membrane, and the carbon dioxide has made its exit into the air sacs. But now, we face a logistical challenge. The blood is the river of life, but it is primarily composed of water. And as we touched upon when discussing the gas laws, oxygen and water do not get along particularly well. If we relied solely on dissolving oxygen into the liquid part of our blood, we would only be able to carry enough to sustain a creature with a much lower metabolism than ours. To live the vibrant, complex lives we lead, we need a specialized transport system. Tonight, we are going to look at the microscopic taxi service of the blood. We are going to explore the brilliant molecule called hemoglobin and the sophisticated chemical disguises that carbon dioxide uses to travel back to the lungs. In our previous session, we watched the silent swap of gases driven by the elegant simplicity of diffusion. Tonight, we take the next natural step in our learning journey by exploring the transport of respiratory gases. This is where biology gets truly clever. We will meet the red blood cell's crowning glory, hemoglobin, and learn why its relationship with oxygen is so famously fickle, and why that fickleness is exactly what keeps you alive. We will also dive into the surprising world of carbon dioxide transport, discovering that the waste gas of our metabolism doesn't just float around. It transforms into a chemical buffer that protects the very pH of our lifeblood. Think of this as the logistics and delivery phase of our course. We are moving from the warehouse of the lungs to the customers, the trillions of cells waiting for their delivery of life. Let's begin with oxygen. Because oxygen is not very soluble in water, about 98.5% of the oxygen in your blood is carried inside red blood cells, bound to a protein called hemoglobin. Hemoglobin is a large, complex molecule made of 4 polypeptide chains, each with a heme group at its center that contains an atom of iron. It is this iron that gives your blood its characteristic red color, and more importantly, its ability to bind to oxygen. I want you to imagine hemoglobin as a specialized taxi with exactly 4 seats. When the taxi arrives at the lungs, the concentration of oxygen is so high that all 4 seats are quickly filled, and we call this fully saturated hemoglobin. But here is the genius of the design. Hemoglobin's attraction to oxygen changes based on its environment. When the red blood cell travels away from the lungs and reaches a tissue that has been working hard, perhaps a muscle or a thinking brain, the environment there is different. It is warmer, it has more carbon dioxide, and it is slightly more acidic. In these conditions, hemoglobin's grip on oxygen weakens. It's as if the taxi driver sees the customer waiting at the curb and decides to open the door. This release of oxygen is what we call unloading. The hemoglobin doesn't just dump its cargo everywhere, it specifically drops off more oxygen in the places that need it most. This relationship is often mapped on what scientists call the oxygen-hemoglobin dissociation curve, and it is an S-shaped graph that shows how hemoglobin cooperates with itself. As soon as the first oxygen molecule binds, the others find it even easier to join. And as soon as the first one leaves, the rest are more willing to follow. Now, let's look at the return trip, the transport of carbon dioxide. While oxygen has its specialized taxi, carbon dioxide is a bit more versatile and a bit more complicated. It has 3 ways of traveling through the blood. About 7% to 10% simply dissolves in the plasma, the liquid part of the blood. Another 20% binds directly to the amino acids of the hemoglobin molecule, though not to the iron seats where oxygen sits. We call this carbamide hemoglobin. However, the vast majority, about 70% of carbon dioxide, undergoes a dramatic chemical transformation. When CO2 enters a red blood cell, it encounters an enzyme called carbonic anhydrase. This enzyme is one of the fastest in the known world. It instantly combines the CO2 with water to form carbonic acid, which then quickly dissociates into a hydrogen ion and a bicarbonate ion. This is a beautiful piece of chemistry. The bicarbonate ion then moves out of the red blood cell and into the plasma, where it acts as a powerful buffer. It helps maintain the blood's pH at a very steady 7.4. So the waste gas from your cells is actually recycled into a protective shield that keeps your blood from becoming too acidic. When the blood finally returns to the lungs, the whole process runs in reverse. The bicarbonate turns back into CO2, which then diffuses out into the alveoli to be breathed away. To truly appreciate hemoglobin, and we have to look at how it responds to the climate of your body. This is often referred to as the Bohr effect, named after the Danish physiologist Christian Bohr. He discovered that when the blood becomes more acidic, usually because of high CO2 levels from exercise, the hemoglobin molecule literally changes its shape. This shape shift makes it much less likely to hold onto oxygen. Think about the elegance of this. When a tissue is working, it produces CO2, which makes the area more acidic. That acidity acts like a chemical signal to the passing red blood cells, telling the hemoglobin, drop the oxygen here. This ensures that your body is a just-in-time delivery system. We don't just spray oxygen everywhere, we deliver it precisely where the metabolic demand is highest. Temperature also plays a role. If you are running a fever, or even if a specific muscle is heating up from use, that heat also weakens the bond between hemoglobin and oxygen. Again, this facilitates the unloading of oxygen exactly where the fire of metabolism is burning. Historically, our understanding of hemoglobin's structure was a gargantuan task. It took the scientist Max Perutz 22 years of painstaking work using X-ray crystallography to map the thousands of atoms in the hemoglobin molecule. He was finally able to show exactly how the 4 subunits of the protein talk to each other to coordinate the binding and releasing of oxygen. For this, he was awarded the Nobel Prize in 1962. It reminds us that even something as simple as a single breath relies on a molecular machine of incredible complexity. There is also a fascinating rivalry in the blood known as the Haldane effect. While the Bohr effect explains how CO2 helps oxygen get off the hemoglobin, the Haldane effect explains how the absence of oxygen helps CO2 get on. When hemoglobin is deoxygenated after it has dropped off its cargo, it actually becomes better at carrying CO2 and buffering hydrogen ions. This means that at the very moment the red blood cell becomes most needed as a trash collector, its capacity to collect that trash increases. The system is perfectly synchronized. As the delivery is made, the pickup becomes more efficient. You can see the importance of this transport system in the way we respond to different environments. For example, why is carbon monoxide so deadly? Carbon monoxide is a cheater. It binds to the iron in your hemoglobin over 200 times more strongly than oxygen does. Once it takes a seat in the hemoglobin taxi, it refuses to leave. Even worse, its presence makes the remaining oxygen molecules stick tighter to the hemoglobin so they can't be dropped off at the tissues. You could have lungs full of fresh air, but your taxis are all full of a passenger that won't get out, leaving your cells to starve. Consider also the phenomenon of blood doping, or even the use of high-altitude training. By increasing the number of red blood cells, and thus the amount of hemoglobin, an athlete can increase the fleet size of their oxygen taxis. This allows them to carry more oxygen to their muscles, delaying the onset of fatigue. Your body does this naturally when you move to the mountains. Your kidneys sense the lower oxygen and release a hormone to trigger the production of more red blood cells. It is a slow, methodical adaptation to the environment. Even as you are resting now, your bicarbonate buffer system is at work. Every time you take a slightly deeper or shallower breath, you are subtly shifting the balance of that CO2 in your blood. If your blood becomes a tiny bit too acidic, your body will instinctively breathe a little faster to blow off more CO2, which pulls the chemical reaction in the other direction and restores the pH. So you see, this isn't just a theory in a book. It's the principle that explains why you can survive at the top of a mountain, why your muscles can perform during a sprint, and why your blood stays in a perfect chemical balance. The transport of gases is the invisible bridge between the physics of the lungs and the chemistry of the cells. It is a masterpiece of molecular cooperation. Take a moment to let that idea find its place. Visualize the millions of hemoglobin taxis in every drop of your blood, opening their doors in the tissues and closing them in the lungs. Picture the carbon dioxide transforming into bicarbonate, silently guarding the pH of your body. It is a complete and dynamic piece of the puzzle. We have now grasped the how of the journey. We know how the gases travel. But who is the conductor of this orchestra? Who tells the heart to beat faster and the lungs to breathe deeper when we start to run? And more importantly, how does your body know to keep breathing while you are in the deep, quiet stages of sleep? So, let's hold that thought here. A complete piece of the story. When we return, we will move into the brain itself to look at the control center. We will begin our study of the neural control of respiration. For now, just rest in the knowledge that your taxis are moving, your buffers are stable, and your body is perfectly fueled. Sleep well, and I will be here to continue our journey when you wake. Lesson 8. Neural Control of Respiration. Tonight we step into the silent command center. Throughout our journey, we have marveled at the plumbing of the airways, the physics of the pressure changes, and the logistics of the hemoglobin taxis. But as you lie there, drifting closer to the edge of sleep, a profound question remains. Who is the conductor of this orchestra? You are not consciously telling your diaphragm to contract twice every 5 seconds. You are not calculating the exact partial pressure of carbon dioxide in your carotid arteries to determine if you need a deeper breath. Yet, the rhythm continues, unfailing, precise, and perfectly tuned to your body's needs. This is the miracle of neural control. It is the bridge between the conscious mind and the ancient, primal autopilot of the brainstem. Tonight, we explore the clusters of neurons that hold the rhythm of your life in their hands. In our last session, we looked at the sophisticated transport systems that carry oxygen and carbon dioxide through the blood. Tonight, we take the next natural step in our learning journey by exploring the neural control of respiration. We are moving from the body's hardware to its software. We will visit the medulla oblongata and the pons, the ancient parts of the brain that house our respiratory centers. We will learn how a group of neurons acts as a natural pacemaker, sending a rhythmic on-off signal to your muscles. We will also discover the lookouts of the system, the chemoreceptors, that constantly taste the blood to ensure its chemistry is just right. Think of this as the study of the brain's most dedicated servant, a system that works tirelessly from your first cry to your final sigh, ensuring you never have to remember to breathe. The control of your breathing is a complex interplay between two different systems: the voluntary control from your cerebral cortex and the involuntary control from your brainstem. While you can choose to hold your breath or sing a long note, the heavy lifting of everyday survival is handled by the autonomic system. The heart of this system lies in the medulla oblongata, located at the very base of your brain where it meets the spinal cord. Inside the medulla, there are two primary groups of neurons that dictate the rhythm. The first is the ventral respiratory group, or the VRG. This is the rhythm generator. Within the VRG sits a cluster of cells known as the pre-Butzinger complex. These cells are the pacemakers of your breath. Much like the cells in your heart that set your pulse, These neurons spontaneously fire electrical impulses. When they fire, they send a signal down the phrenic and intercostal nerves, telling your diaphragm and ribs to contract. This is the 2-second inhale phase. Then they stop firing, allowing the muscles to relax for the 3-second exhale phase. It is a simple, elegant on-off switch that repeats roughly 12 to 15 times every minute while you are at rest. The second group in the medulla is the dorsal respiratory group, or the DRG. While the VRG sets the pace, the DRG acts as the integration center. It receives input from all over the body, from your lungs, your blood vessels, and even your joints. It takes all this data, processes it, and then nudges the VRG to adjust the breath accordingly. Above the medulla lies the pons. The pons houses the pontine respiratory group, which acts as a smoother. Without the pons, your breathing would be jerky and gasping. The neurons here ensure that the transition between inhaling and exhaling is fluid and rhythmic. They also help limit the duration of inspiration, preventing the lungs from overinflating. Think of the medulla as the drummer setting the beat, and the pons as the conductor ensuring the melody is graceful and perfectly timed. However, a rhythm is only useful if it can change to meet the body's demands. This is where the sensory feedback loop comes in. Scattered throughout your body are specialized sensors called chemoreceptors. The central chemoreceptors are located right in the medulla, while the peripheral chemoreceptors are found in the high traffic areas of your vasculature, the aortic arch, and the carotid arteries. These sensors are constantly tasting the blood and the cerebrospinal fluid. Interestingly, they aren't primarily looking for oxygen. Their main focus is on carbon dioxide and the concentration of hydrogen ions, which reflects the acidity of your blood. Because CO2 can easily cross the blood-brain barrier, it is the most powerful stimulus for breathing. If the level of CO2 rises even slightly, the chemoreceptors send an urgent signal to the brainstem. The air is getting stale, pick up the pace. In response, the medulla increases the frequency and depth of the signals to your muscles. You breathe faster and deeper, blowing off the excess CO2 until the chemistry returns to its perfect baseline. While CO2 is the primary driver, oxygen does play a role, but usually only in extreme circumstances. Our peripheral chemoreceptors in the carotid bodies do monitor oxygen levels, but they don't generally sound the alarm until the partial pressure of oxygen drops quite significantly, from a normal 100 millimeters of mercury down to about 60 millimeters of mercury. This is a fail-safe system. Your body trusts the CO2 levels to guide the day-to-day rhythm, but it keeps an eye on oxygen as a backup for high altitudes or respiratory distress. There is also a fascinating protective reflex known as the Hearing-Breuer reflex. Deep within the smooth muscle of your bronchi and bronchioles are stretch receptors. As you take a very deep breath and your lungs expand, these receptors are pulled taut. When they reach a certain threshold, they send an inhibitory signal back to the medulla, telling the inspiratory neurons to shut off. It is a biological safety valve that prevents the lungs from being overdistended. It's a beautiful example of how the organ being moved, the lung, has a direct say in how the mover, the brain, behaves. Historically, our understanding of these centers was gained through the meticulous work of 19th and early 20th century physiologists. They used lesion studies, carefully observing how breathing patterns changed when different parts of the brainstem were damaged. For instance, if the connection between the pons and the medulla is severed, a strange pattern called apneustic breathing occurs, where the subject takes long, gasping inhalations and very short exhalations. And this taught us that the pons is essential for turning off the inhale. The discovery of the Prey-Butzinger complex is a much more recent triumph, identified only in the late 1980s by Jack Feldman and his team. This tiny cluster of neurons changed our entire understanding of the breath. It proved that breathing is not just a response to the environment, it is an inherent internal rhythm that is hardwired into our very being. It is the drumbeat of our existence. Furthermore, we must consider the role of the hypothalamus and the limbic system. Have you ever noticed how your breathing hitches when you are startled, or how it becomes rapid and shallow when you are anxious? Your emotional state has a direct hotline to your respiratory centers. The hypothalamus can bypass the normal rhythm to prepare you for fight or flight, increasing your ventilation before your CO2 levels even have a chance to change. Similarly, when you are in a state of deep, calm relaxation, like you are right now, your limbic system sends soothing signals that allow the medulla to drop into its slowest, most efficient sleep rhythm. You can observe this neural control in the simple act of holding your breath. Try it for a few seconds, and you will feel a growing urge to breathe. That isn't actually a lack of air you are feeling. It is your chemoreceptors sensing the rapid buildup of CO2 in your blood. Eventually, that signal becomes so powerful that it overrides your voluntary control. Your brainstem literally reboots the system, forcing you to take a breath. This is why it is impossible to hold your breath until you die. Your medulla is the ultimate guardian of your survival. This also explains the danger of shallow water blackout in swimmers. If a swimmer hyperventilates before diving, they blow off so much CO2 that their levels are artificially low. As they swim underwater, their oxygen levels drop dangerously. But because their CO2 levels haven't yet risen enough to trigger the urge to breathe, they don't realize they are in trouble. They can lose consciousness from lack of oxygen before their brainstem ever tells them to surface. It is a sobering reminder that our autopilot relies on specific chemical cues to keep us safe. Even the common hiccup is a glitch in this neural wiring. A hiccup is a sudden, involuntary contraction of the diaphragm, followed by the rapid closure of the vocal cords. It is essentially a misfire of the phrenic nerve. While they are usually harmless, they show us how much we rely on the precise, millisecond by millisecond timing of the signals coming from the medulla. As you lie here now, your neural control is transitioning. As the noise of the day fades away, your cerebral cortex, the part of you that thinks and plans, is stepping back. The voluntary control is shutting down, and you are handing the keys of your life over to the ancient wise neurons of your brainstem. They will monitor your CO2, they will smooth out the transitions, and they will keep the rhythm going while you dream. You don't have to do a thing. You are being breathed by the universe. Take a moment to let that logic find its place in your mind. Visualize those tiny clusters of neurons in your brainstem firing in a steady rhythmic pulse. Feel the smoother in the pons, ensuring each breath is a gentle wave. It is a complete and reassuring piece of the puzzle. We have now grasped the control center of the system. We know how the rhythm is set and how it is monitored. But how does this system respond when the world changes? What happens when we push our bodies to their physical limits? Or when we travel to the thin, cold air of a mountain peak? So let's hold that thought here. When we return, we will look at the system's incredible capacity for change. We will begin our study of the respiratory adaptations to exercise and high altitude. For now, just let the autopilot take over. Trust in the wisdom of your medulla. Your rhythm is perfect, your chemistry is balanced, and you are safe. Sleep well, and I will be here to continue our journey when you are ready. Lesson 9. Respiratory adaptations to exercise and high altitude. As we move toward the final stages of our study, I want you to consider the incredible flexibility of the human form. Up until now, we have largely discussed the respiratory system in a state of rest, the quiet, rhythmic breathing you are experiencing at this very moment. But life is rarely static. We are creatures of movement, of ambition, and of exploration. Sometimes we push our muscles to their absolute limits in a sprint. And sometimes we travel to the roof of the world, where the air is thin and the cold is biting. In these moments, the respiratory system doesn't just work harder, it actually changes. It adapts. It upgrades itself to meet the challenge. Tonight, we explore the remarkable plasticity of your breath, how it handles the fire of exercise and the scarcity of the high mountains. In our previous session, we went deep into the brainstem to find the conductor of the respiratory orchestra. Tonight, we take the next natural step in our learning journey by exploring respiratory adaptations to exercise and high altitude. We are going to look at how the body shifts from a low-power resting state to a high-performance mode during physical exertion. We will learn that getting out of breath isn't a failure, but a highly coordinated success. Then, we will turn our gaze upward to the peaks of the Himalayas and the Andes to see how the body survives when the very air it depends on begins to vanish. We will explore the difference between a quick adjustment and a long-term biological transformation. Think of this as the stress test of the respiratory system, a study in how a masterpiece of engineering responds to the extremes of life. Let's begin with the immediate challenge of exercise. When you start to move vigorously, your muscles become tiny furnaces. They consume oxygen at a staggering rate and pour carbon dioxide and heat into your bloodstream. To keep the fire burning, the respiratory system must ramp up its delivery and its waste removal. This increase in the rate and depth of breathing is what we call hyperpnea. Interestingly, your body doesn't wait for the chemistry of your blood to turn bad before it acts. As soon as your brain sends the signal to your muscles to move, it simultaneously sends a heads-up signal to your respiratory centers in the medulla. This is a feed-forward mechanism. Additionally, sensory receptors in your moving joints and muscles, called proprioceptors, send instant alerts to the brain, saying, "Activity has begun." Because of this, your breathing rate increases the very second you start to run, often before your CO2 levels have even moved. It is a proactive system, anticipating the need rather than just reacting to a crisis. During intense exercise, your ventilation can increase from a resting 5 or 6 liters of air per minute to over 100 liters per minute in a trained athlete. And this is achieved by using the inspiratory reserve volume, the extra space in your lungs you don't normally use, and by recruiting accessory muscles in your neck and chest to pull in even more air. At the same time, the blood flow to the lungs increases, and the capillaries that were closed during rest suddenly open up. This ensures that every bit of that extra air has a chance to meet the blood. Now, let's consider the challenge of the mountains. As we learned in our session on gas laws, the percentage of oxygen in the air stays the same, about 21%, regardless of how high you climb. However, the total atmospheric pressure drops. At 18,000 feet, the air pressure is only half of what it is at sea level. This means the partial pressure of oxygen is also cut in half. There simply aren't enough oxygen molecules to push their way across your respiratory membrane effectively. When you first arrive at a high altitude, your body responds with acute mountain sickness. Your chemoreceptors sense the drop in oxygen and trigger an immediate increase in breathing. But there's a catch. By breathing faster to get more oxygen, you blow off too much CO2. This makes your blood more alkaline, which actually tells your brain to slow down your breathing. Your body is essentially having an internal argument. The oxygen sensors are shouting faster, while the CO2 sensors are whispering slower. For the first few days, you feel winded, fatigued, and perhaps a bit nauseated as your body tries to find a new equilibrium. If you stay at that high altitude, however, a magnificent process called acclimatization begins. This is where the short-term fixes turn into long-term structural changes. The first hero of this story is the kidney. Your kidneys sense the drop in oxygen and the shift in blood pH. They respond by releasing a hormone called erythropoietin, or EPO. EPO travels through your bloodstream to your bone marrow, where it gives a very specific command: produce more red blood cells. Over the course of a few weeks, your fleet of hemoglobin taxis increases significantly. This is why people who live at high altitudes have blood that is much thicker with red cells than those at sea level, even if each taxi is only half full of oxygen. Having twice as many taxis means the total delivery to the tissues remains the same. Furthermore, the cells themselves adapt. Your muscles begin to produce more mitochondria, the power plants of the cell, and more myoglobin, a protein that stores oxygen directly in the muscle tissue. This makes the unloading of oxygen from the blood even more efficient. It is a total system upgrade, from the lungs to the blood to the very microscopic interior of your cells. Historically, our understanding of these adaptations was forged through daring high-altitude expeditions. In the 1920s, during the early attempts to climb Mount Everest, scientists were obsessed with whether a human could survive at 29,000 feet without supplemental oxygen. Some argued the diffusion limit of the lungs would make it impossible. It wasn't until 1978, when Reinhold Messner and Peter Habeler reached the summit without bottled oxygen, that we realized just how powerful the body's acclimatization could be. They proved that with enough time to adapt, the human lung can perform miracles in thin air. There is also a fascinating genetic layer to this story. In populations that have lived at high altitudes for thousands of years, such as the Tibetans in the Himalayas or the Quechua in the Andes, we see different evolutionary strategies. Tibetans, for example, don't actually produce more red blood cells. Instead, they have evolved to breathe much faster than sea-level humans and have wider blood vessels to move blood more quickly. This avoids the sludge effect of overly thick blood while still delivering enough oxygen. It shows that there is more than one way for the respiratory system to solve the problem of survival. You can see the results of these adaptations in the world of professional sports. This is why altitude training is a staple for Olympic runners and cyclists. By living and training at 6,000 or 7,000 feet for several weeks, they force their bodies to produce more EPO and more red blood cells. When they return to sea level for a race, they still have that extra fleet of taxis. For a short window of time, they are essentially super oxygenated, allowing them to run faster and longer before they hit their limit. Think also about the sensation of a second wind during a long walk or run. This is a synthesis of everything we've learned. It is the moment when your heart, your lungs, and your blood vessels finally coordinate their efforts. Your bronchioles have dilated, your capillaries have opened, and then your hemoglobin is unloading oxygen at the perfect rate. The struggle of the first few minutes fades away as the system finds its high-performance rhythm. Even as you are resting now, your body is maintaining its capacity for these changes. If you were to stand up and start sprinting right now, your brainstem wouldn't be surprised. It has the exercise software ready to run. And if you were to board a plane to a mountain village tomorrow, your kidneys would be ready to start the slow work of acclimatization. So you see, this isn't just a theory in a book. It's the principle that explains why you can climb a flight of stairs, why you can hike a trail, and why the human species has been able to inhabit every corner of the globe, from the sea-level tropics to the frozen highlands. The respiratory system is not a rigid cage. It is a dynamic, living response to the world. It is a masterpiece of flexibility that ensures that no matter where you go or how hard you push, the breath of life will follow you. Take a moment to let that idea find its place. Visualize your blood slowly becoming richer as it adapts to the heights. Feel the proprioceptors in your joints, ready to alert your brain the moment you move. It is a complete and inspiring piece of the puzzle. We have now seen the system in its peak performance and its most rugged adaptations. We have followed the air from the nose to the blood, and from the quiet of sleep to the fire of exercise. But to truly understand any masterpiece, we must also look at what happens when the design is challenged by illness or injury. For our final lesson, we will look at the vulnerabilities of this elegant system. So, let's hold that thought here. When we return, we will conclude our journey by looking at the challenges that can disrupt this harmony. We will begin our study of the pathophysiology of the respiratory system. For now, just rest in the knowledge that your body is built for resilience. Your lungs are adaptable, your blood is capable, and you are perfectly equipped for the journey of life. Sleep well, and I will be here to conclude our course when you are ready. Lesson 10, Pathophysiology of the Respiratory System. We have arrived at the final stage of our journey together. Over the course of our previous 9 lessons, we have marveled at the sheer elegance of the respiratory system, the way it warms the air, the physics of its movement, and the microscopic dance of gas exchange that sustains every cell in your body. But to truly understand a masterpiece of engineering, one must also look at how it responds to stress, wear, and interference. Tonight, we conclude our crash course by looking at the vulnerabilities of the system. We explore pathophysiology, the study of how normal physiological processes are altered by disease. By understanding what happens when the plumbing clogs or the membranes fail, we gain a deeper, more profound appreciation for the silent, imperfect work your body is doing right now. In our last session, we looked at the incredible resilience of the lungs, how they adapt to the fire of exercise and the thin air of the mountains. Tonight, we take the final natural step in our learning journey by exploring the pathophysiology of the respiratory system. We are going to look at the three main ways the system can be compromised. We will discuss obstructive disorders, where the pathways become narrow and difficult to navigate. Restrictive disorders, where the lungs lose their ability to expand. And gas exchange disorders, where the microscopic border between air and blood is breached. We will look at common conditions like asthma, COPD, and pneumonia, not as frightening diagnoses, but as mechanical puzzles that help us see the brilliance of the healthy state. Think of this as the maintenance and repair manual for your life's most vital engine. To make sense of the vast world of respiratory illness, clinicians generally divide disorders into two broad categories: obstructive and restrictive. Obstructive disorders are characterized by a hindrance to the flow of air, particularly during exhalation. Imagine trying to breathe through a straw that has been pinched in the middle. You can get the air in if you try hard enough, but getting it back out takes a long time and a great deal of effort. The most common example of this is asthma. In an asthmatic response, the smooth muscle surrounding the bronchioles becomes hypersensitive to triggers like pollen, cold air, or stress, and it contracts sharply. At the same time, the lining of the airway swells and produces excess mucus. This creates a bottleneck in the bronchial tree. Because the air can't leave the lungs easily, it gets trapped, making the next breath even harder to take. Chronic obstructive pulmonary disease, or COPD, is another major obstructive condition, usually representing a combination of two problems: chronic bronchitis and emphysema. In chronic bronchitis, the mucociliary escalator we discussed in Lesson 2 becomes overwhelmed. The mucus-producing cells grow in number and size, leading to a persistent productive cough and narrowed airways. Emphysema, however, is a disease of the grapes themselves, the alveoli. In a healthy lung, you have millions of tiny alveoli, which provides that massive surface area for gas exchange. In emphysema, the walls between these tiny sacs break down. Many tiny bubbles merge into a few large, flabby ones. While it might seem like more room would be a good thing, it is actually a disaster for physics. It drastically reduces the surface area where oxygen can meet the blood. And because the lungs lose their elastic snap, the patient has to use their abdominal muscles just to force the air out. It turns the effortless act of breathing into an exhausting, full-body workout. On the other side of the coin are restrictive disorders. These are conditions where the total lung capacity is reduced because the lungs or the chest wall cannot expand. This is like trying to inflate a balloon that has been wrapped in duct tape. The pathways might be clear, but the container is too stiff. This can happen through pulmonary fibrosis, where healthy, spongy lung tissue is replaced by stiff, non-functional scar tissue. It can also happen due to external factors like extreme obesity or structural changes in the rib cage, which physically prevent the diaphragm from doing its work. Finally, we have disorders of gas exchange, such as pneumonia. Pneumonia is essentially an inflammatory flood in the lungs. When bacteria or viruses take hold in the alveoli, the body responds by sending white blood cells and fluid to the area. Remember that 0.5 micrometer respiratory membrane we studied? In pneumonia, that membrane is submerged in fluid. Oxygen, which is not very soluble in water, simply cannot make the jump into the blood. This is why gas exchange disorders are so critical. They strike at the very heart of the system's mission. To understand why these conditions are so impactful, and we have to look back at the ventilation-perfusion coupling we learned about earlier. In a healthy person, the brain stem ensures that blood only goes to the parts of the lung that have fresh air. In many respiratory diseases, this coupling breaks down. This leads to what we call a V over Q mismatch. Imagine a part of the lung that is filled with fluid from pneumonia. If the body keeps sending blood to that area, that blood will leave the lung without any new oxygen. When it mixes back in with the good blood from other parts of the lung, it dilutes the total oxygen concentration. This is why doctors monitor oxygen saturation. It is a measure of how effectively the system is overcoming these microscopic mismatches. Historically, our ability to diagnose these conditions was transformed by the invention of the spirometer in the mid-19th century by John Hutchinson. He was the first to realize that, by measuring the volume and the speed of the air a person could exhale, he could tell exactly what kind of mechanical problem they had. If a person could breathe out a lot of air, but did it very slowly, he knew it was an obstructive problem. If they breathed out very quickly, but had very little air to give, he knew it was a restrictive problem. This simple test, the pulmonary function test, remains the gold standard for respiratory medicine today. Another layer to consider is the role of sleep apnea, a condition that perfectly illustrates the neural control we discussed in Lesson 8. In obstructive sleep apnea, the soft tissues of the throat relax so much during sleep that they physically block the airway. The person's bellows, the diaphragm, are working, but the door is closed. The CO2 levels in the blood begin to rise sharply, eventually triggering an emergency reboot from the brain stem that jolts the person awake just enough to open the airway. It is a nightly battle between the need for sleep and the need for air, and it highlights just how vital that patent or open airway is to our survival. We should also mention the remarkable progress in treating these conditions, from the development of bronchodilators that unlock the smooth muscle in asthma to the creation of tiny mesh-like stents that can keep airways open. Modern medicine is a testament to our understanding of respiratory anatomy. And we have even mastered the art of extracorporeal membrane oxygenation, ECMO, where a machine takes the blood out of the body, performs the gas exchange itself, and sends it back, essentially acting as a temporary external pair of lungs. It is the ultimate backup system for the most severe cases of respiratory failure. You can see the relevance of pathophysiology in the very air we breathe. This is why air quality alerts and anti-smoking campaigns are so critical. The respiratory system is incredibly robust, but it is also open to the environment. Unlike your heart or your kidneys, which are tucked safely away, your lungs are in direct contact with the outside world. Every pollutant, every puff of smoke, and every virus is a direct challenge to that zero point 0.5 micrometer membrane. Consider the simple act of a cough. Now that you know the anatomy, you can see a cough for what it is. A high-pressure blast designed to clear an obstruction. Your vocal cords close tight. Your abdominal muscles contract to create massive pressure in the chest. And then the vocal cords snap open, creating a gust of air that can travel at speeds of up to 50 miles per hour. It is a violent, necessary defense of the lower respiratory tract. Think about why we feel short of breath when we are sick. It isn't just that your lungs are struggling. It's that your brainstem is receiving a constant stream of alarm signals from those chemoreceptors and stretch receptors. Your autopilot is trying to compensate for the fluid in your alveoli or the narrowing of your bronchioles. That feeling of air hunger is the conscious mind's interpretation of a system-wide effort to maintain homeostatic balance. Even as you are resting now, your body is performing routine maintenance to prevent these pathologies. Your alveolar macrophages are patrolling for dust. Your type 2 cells are replenishing the surfactant to prevent collapse. And your ciliary escalator is moving tiny particles of dust up and away. You are experiencing the perfect state of respiratory health. A state where the pathways are clear, the membranes are thin, and the exchange is effortless. So you see, this final lesson is not about the fear of disease, but about the triumph of health. By seeing where the system can falter, we see more clearly the genius of its design. The respiratory system is a masterpiece of redundancy, flexibility, and resilience. It is the foundation upon which the rest of your life is built. Take a moment to let that entire journey find its place in your mind. From the first inhale through the nasal conchae to the microscopic hop of oxygen into the hemoglobin taxi. And finally to the protective mechanisms that keep the system running. You have now completed the full circle of our crash course. We have explored the why, the where, and the how. You have looked at the world of anatomy and physiology through the eyes of a mentor and a scientist. But more importantly, you have spent this time connecting with the very rhythm that keeps you alive. You are no longer just a person breathing. You are a person who understands the miracle of the breath. I have handed you all the pieces of the puzzle. The story of your respiration is now yours to keep. There are no more lessons to learn tonight, only the quiet, rhythmic reality of your own health. As you drift into a deep and restorative sleep, remember that your body is a masterpiece that knows exactly how to care for itself. Your lungs are clear, your heart is steady, and your mind is at peace. I have enjoyed being your guide on this journey. Perhaps in the future, we will explore another system of the body together. But for now, the lesson is over. The autopilot is engaged. You are safe, you are knowledgeable, and you are ready for rest. Sleep deeply, my friend.